Hi, everyone. This is Chen from IBM Research. Welcome to our presentation of holistic adversarial robustness of deep learning models. This is a joint work with Sijia from Michigan State University. So the motivation of our paper is actually try to address the gap between AI development and deployment. And in particular, we know when we develop AI, we assume the environment is ideal, like data are RID, and there are no noise, and models are fully trained and designed, and so on. But in reality, when we deploy the AI in the wild, we will encounter many challenges, like natural data shifts or even adversarial threats in the wild. So studying adversarial robustness will effectively help us to evaluate and mitigate the gap between development and deployment. So one important motivation of adversarial robustness is motivated from these adversarial threats by bad actors. So a recent Gartner report has predicted that the recent cyber attacks will target the function of AI technology in the recent systems, including a lot of the attacks that we will be introduced in this presentation. However, the recent study also shows most of the industries are not ready to secure their systems against these advanced attacks. So why do we care so much about adversarial, or in other words, the worst case robustness? So the importance is that we would like to prevent prediction evasive manipulation on the deployed machine learning systems. And no matter what your role is in the AI technology, I believe everybody should understand and even practice adversarial robustness. So for example, there are many failure modes or these negative use cases that has been demonstrated over time that will attract users' attention and eventually make the users intended not to trust the AI service that we provided. And these examples include digital adversarial examples as well as the physical world scenarios that will try to manipulate the data inputs and make the machine learning model make incorrect decision-making process, including the recent ChatGPT that could be misguided or misled by users' intended questions. And if you are a model developer, you will be very curious to understand the negative impacts possibly in the AI service you are going to provide, especially for high stakes and safety critical tasks. And most importantly, understanding the lack of adversarial robustness could help you understand the limitation and further improve the performance of your machine learning models. And if you're a model developer, you would, of course, would like to use this adversarial robustness toolkits to prevent possible loss and failures in revenue and reputation and ensure safe and responsible use in our AI technology. And there are also many databases and collected resources to report real-life exploits, vulnerabilities, and incidences caused by lacking robustness of our AI technology, like adversarial machine learning threat matrix and AI incidents database. So this paper is based on our portfolio in adversarial robustness research over the years, and as well as a collection of important topics and ideas developed in this field. So the purpose of this paper is to provide an entry-level survey-like tutorials to help interested researchers or users who wants to enter this field or understand the concept by introducing the terms and terminologies and some research methodologies and evaluation principles that we have been using for studying and improving adversarial robustness. So I should comment that this is one of the very few fields that actually caught attention, including to everyone, including academic researchers, industrial researchers, as well as the general audience. And the adversarial robustness that will be covered in this paper actually includes 4 different dimensions, including attack, defense, evaluation and certification, and novel applications. So what do we mean by holistic adversarial robustness? So we would like to bring to you the picture of AI lifecycle, which is divided into 2 phases, training phase and deployment phase. In the training phase, the user will select data and select which model to train on those data. So when the model is fully trained and tuned, we will deploy the model as a service. And there are also different modes of deployment, right? So in the typical API setting, the model is deployed as a black box model, so such that the users can use the service, but the user would not know what is actually behind the service. On the other hand, in a scenario like a Hugging Face settings, the model is transparent to the user. The user can download the model and use it for its own purpose. In this case, the model is a white box model because everything is known to the user. So depending on what could be go wrong or what's our assumption on attackers can do in the AI lifecycle, there are correspondingly different types of adversarial attacks and categories. So for example, training phase attack basically assumes attackers has the ability to manipulate part of the training data and understand some knowledge of the training method or model. On the other hand, for the deployment time attack, like evasion attack, the attacker does not have the ability to manipulate training data, but it may know some partial information or receive some feedback from the model it is attacking until and use that information to successfully find an adversarial example to evade the prediction of the model. And of course, adversarial robustness also incorporates classical security topics like extraction attack, model stealing, membership inference, data privacy, and so on. And it also includes more recent advances for AI governance and trustworthy AI policy making and ethics. So in a high level, adversarial attacks is actually a way to help model developers or to help white hat hackers to find failure modes and also to help them to understand the limitations of the models they are developing. So this includes developing practical robustness testing tools to find failure modes in both white box and black box settings, and also a demonstration of those failure examples for different data modalities and different machine learning models in both digital and physical world. So in what follows, I will show some examples. So this is one example that we created, we call adversarial t-shirt. So whoever is wearing the t-shirt with the pattern that we designed will basically become invisible to a deep learning-based person detector, that it will show a frame of detecting a person will disappear in most of the frames. So similarly for image captioning, which takes image as an input and will output a caption describing the content. In this scenario, on the top is the original image, and the system will be able to generate very precise content, a red stop sign sitting on the top sign of a road. However, when we slightly perturb the image, then the corresponding caption will be changed to a brown teddy bear laying on top of a bed. So this example shows the model is basically overly sensitive and may lack some fundamental understanding of the contents in the image. Another use case is we can use this tool to understand how easy it is to evade the prediction of our detector, like a fake news detector or spam detector. So for example, given a text paragraph, an adversarial attack can basically try to modify very few amount of words or sentences while preserving the semantic meaning and tries to evade the prediction of a fake news detector. So it is very important if your goal is to develop a robust fake news or spam detector, you will certainly like to try out these adversarial attacks to show how reliable or how sensitive your model is to these perturbations in the specific domains. So let's do a deep dive into different types of attacks, right? So first one is the inference deployment phase attack. In this case, we assume the model is fixed, fully trained and fixed, and the goal is to manipulate the data inputs to find adversarial examples. And there are also different scenarios of finding adversarial examples to create evasion attack. So white box attack means everything is transparent to the attacker, and in the black box scenario, soft label attack means both the prediction and the confidence is known to the attacker, whereas hard label attack assumes only the prediction label is known to the attacker. And there's also transfer attack that basically allows a attacker to find adversarial examples in their own white box surrogate model and will transfer their adversarial example to the target black box model. So all in all, the attack formulation can actually be well formulated in some optimization perspective, where the design variable is what you would like to manipulate your data sample. For example, as simple as a image perturbation. So the high-level idea will be finding a perturbation such that the similarity between the original sample and the perturbed sample remains high, but the perturbed sample will have a different property than the original sample. So for example, wrong prediction as an example, or being predicted as a specific class label. And depending on how you formulate this attack problem, right, the minimizing the distance subject to some attack criterion, or minimizing the attack loss subject to some distance criterion, there are correspondingly different types of attack methods. And in general, for images, there are also some popular LP norm perturbations to evaluate the image similarity. Like L-infinity norm will capture the maximum perturbation in each dimension, and L1 norm captures the total variation. L0 norm captures the number of changes we made in the input dimensions, and so on. And for more details, please refer to our paper. So similarly, for training phase attack, in this case, the attacker would like to manipulate or change part of the training data such that whatever model trained on those data will carry certain property that can be exploited by an attacker. So backdoor attack is a typical example where the attacker will inject some trigger pattern, like what we show, some white square pattern on the right bottom side of the image, and it will be attached to parts of the training data. And the modified samples will also be associated with the same target label, digit 4, regardless of its true content. So because of the mineralization effects, right? So whatever deep learning model trained on this poison data will carry a backdoor effect in the sense that for data inputs with this trigger pattern, it will be classified as a 4 because the model thinks this trigger pattern is a very important feature associated with the label 4. However, without the trigger pattern, the backdoor model just behaves like a regular model and can do a correct digit classification. So it is called a backdoor because you will only know your model has been compromised when the activation pattern has been activated. And the same threat model can also be amplified, and the risk can be amplified in some federated learning scenarios where multiple agents holding private data wants to jointly train a global model with limited information sharing. In this case, backdoor attack can be even more successful, and it can also evade some robust federated learning scenarios. So moving on to defenses, right? So there are empirical and provable robustness for defenses depending on the usage and the applications that you care about. So geometrically, we can understand adversarial example as some data sample given a fixed decision boundary, some data sample that lies very close to the original data sample, so they look alike, but they actually sit on different decision regions. That's why they will give different classification prediction. So the notion of robustness is generally tied to how close to measure the distance between a data sample to the closest decision boundary, which is also known as the concept of a margin. So we can actually quantify robustness by understanding the local margin of a given set of data samples. And there are also many studies tries to improve adversarial robustness empirically for a model. And over the years, some of the heuristic proposals has been broken by more advanced attacks or has shown some limited improvements. So by far, one of the most effective methods will be what we call adversarial training, which actually requires when we train a model, train the model parameters, we actually generate these adversarial examples on the fly and ask the model parameters to be updated such that the loss evaluated on those adversarial examples can be mitigated. So this is one of the most effective methods so far, but there are also some downsides, like it is not really scalable to large models or data sets, and there is a notable trade-off between the original utility, like test accuracy, versus the improved robustness. So in a more high level, defenses can also be divided into two types. The first type is detection, that tries to either given a model or given an input, that try to detect whether a model has a backdoor or whether this given input is an adversarial example or not. And there's another type is patching, right? So how can we do some methods or apply some operations or take some actions to improve the robustness of a given model, like adversarial training. Finally, I would like to cover robustness certification evaluation. So it is related to provable certified robustness. In this case, we are interested in knowing how can we quantify a safe region of a given data sample, such that we can show that no matter how the sample is modified, as long as the modified sample still lies in the specified safe region, then we can guarantee the prediction of the sample will not be changed after manipulation. And therefore, the model is attack-proof with respect to the modification being made, as long as the modification is smaller or within the certified region. So geometrically, we can understand certification by again, through the notion of a margin-based adversarial robustness studies. So any adversarial example will be considered as an upper bound to the smallest perturbation required to flip the label. And for verification, we actually aim to find a certified region that will show that no matter how we move a sample, as long as the sample is still within that region, then the model prediction will be consistent. So it actually provides a lower bound on the minimum perturbation required to flip the label. So you can see that now this, because of this different notion of lower bound and upper bound, some application will require certifying some level of lower bound, while some application simply requires finding a counterexample of finding one successful adversarial example to show the model is not robust enough. So finally, I would like to conclude a roadmap toward holistic adversarial robustness. So we believe to achieve adversarial robustness, the tools should be made as model agnostic as possible, right? It should apply to different machine learning models. At the same time, it should also leverage the data and domain-specific knowledge as much as we can. And it also needs to be practical, right, to mitigate the trade-off between utility and improved robustness. So the whole process, right, should actually be evaluated and practiced through the AI lifecycle, including training, testing, and monitoring. And the terminologies specific to adversarial robustness actually carry a broader notion. For example, attack can be mapped to finding bugs in our systems. Defense can be mapped to hardening our systems. Verification can be mapped to certifying or providing performance guarantees for our system. And more interestingly, there are also a lot of noteworthy applications through studying and have a better understanding of adversarial robustness for deep learning models. So if you are interested in knowing more about this topic, right, please check out the online tutorials and also some open source libraries that are available for you to evaluate and improve the robustness of your own model. And also, we also listed some sample survey papers, including this paper that we presented at AAAI 2023, and also a book that I recently published with Professor Chorei Xie at UCLA. So thank you again for listening to our talk, and you know how to reach out to us if you have any questions regarding this paper and or this domain. Thank you.